Hey everybody, this video is for us to use the ratio and root test in order to determine the absolute convergence or divergence of infinite series. So as we've already talked about, you know if a series is going to absolutely converge, then it's also going to converge. In this video, you're going to see two different ways in which the ratio and root tests are both kind of demonstrated. One is from my own class notes, and then another is from the textbook. You'll see that they are pretty much the same, just a different way of writing it, and I'll show different things throughout this video of how to write the explanation for this. So these are our last two tests of testing for convergence and divergence for infinite series. So hope you enjoy the video and come prepared to class to do some problems related to ratio and root test. So here's the ratio test in so many words, and you can pause this and read it. I'm not going to read each one, but the main thing about the ratio test is that we are finding the limit of the absolute value of a ratio, where here's a sub n. We're going to take the a sub n plus first term and divide it by a sub n, and that's true for all conditions. Alright, if we take that limit as n goes to infinity and we get some value less than 1, then it converges absolutely. If we get, we use that same ratio, called the ratio test, and we get something greater than 1 or infinity, then it diverges, as it says here. And as you will see later, and I'll give some examples, if the ratio test is inconclusive, if that limit is equal to 1. So if it's inconclusive and we still have to determine convergence or divergence, that means we're going to have to go and use another test, possibly, in order to determine the convergence or divergence. The next slide is the theorem right out of your textbook. So you can see this in your textbook in chapter, I think it's 10.5 for you, and it's the same thing. Now you'll see me use this notation rho, this Greek letter, as the limit. It's just an easier way to kind of explain it. I kind of do it a couple different ways, and you can pick whichever one you feel is most comfortable for you. All right, so let's get to it. So here's our first series that we're going to determine convergence or divergence. All right, so what the first thing I'm going to do is I'm going to determine that ratio. So without any further interruption, I'm going to show you. All right, there's my a. So my a n plus first term is going to be this, but it's going to be my n plus first term. So it's going to be 2 over n plus 1 over n plus 1 factorial, all over my a sub n, which is right here, 2 over n factorial. And if I rewrite that, you're going to see that this is equal to, remember, we had to multiply by the reciprocal. And this is where students actually have the most trouble, is trying to simplify this and understand what's kind of going on. So let me show you something. N plus 1 factorial, what does that really mean? Well, that means n plus 1 times n minus 1 times, and on and on and on. So it's really equal to n plus 1 times n factorial. N factorial being the rest here. So that's what we're dealing with right there. So if we were to rewrite that right below it as n plus 1 times n factorial, you can see what happens with this n factorial. They go goodbye-bye. All right. So what happens to this? What does 2 to the n plus 1 equal to? Well, it's really equal to 2 to the n times 2 to the 1, because when you multiply like bases, you add the exponents. So this is really 2 to the n times 2 to the 1. This is 2 to the n, and look at that. Boom. So really, this term ends up being 2 over n plus 1. So I did the work outside of the limit. And, you know, I'm stressing notation, so I do all that work outside of the limit, not finding the limit. So now I go my limit as my absolute value of a to the n plus 1, a sub n plus 1, I'm sorry, is really equal to the limit as n approaches infinity of 2 over n plus 1. Evaluating this limit, you're going to see that that is equal to 0. So since this is equal to 0, that's at rho from here, okay, that's where I'm getting it. It's one way you can do it, is equal to 0, which is less than 1, the series 2 to the n over n factorial, as n goes from 0 to infinity, converges, or more specifically, converges absolutely. Okay, so that is how you apply that ratio test and using that condition. Moving on, we are going to do the same thing right here. We are going to first find that ratio for this. So this becomes n plus 1 quantity squared over to the n plus 1. Now I'm going to multiply by that reciprocal right away. You know that. I'm not going to do that over and over again, which gives you this. All right. We know how this cancels out because we talked about it already before. So that we're going to be left with just 2 in the denominator, right? Because 2 to the n will cancel out. This guy and 2 to the n's will just be left with 2. All right. So we're going to be left with 2n squared. And I'm going to FOIL the top. And when I do that, this is what I get. All right. So there's my ratio. So let's take this limit now. As n approaches infinity, of the a sub n plus 1 a sub n, which is equal to the limit absolute value. And you should already see, probably by looking at this, that you're going to get a limit that is equal to 1/2. 1/2 is less than 1. So since, and I'm just writing it a different way. You can see I'm actually writing a little bit more explicitly here. Is less than 1, the series, the summation is n equals 1 to infinity of n squared over 2 to the n, converges absolutely, and therefore converges by the ratio test. It's good to note that what test we're using, ratio test, especially since we're going to be doing 2 tests today. Okay? Moving on. Here's that next one. You can see here that we have this, it looks like an alternating series. Does that matter? It does not matter that it's an alternating series because we're taking the absolute value, right? So if I'm going to start down here, and I'm actually going to take the absolute value of that ratio from the beginning. I'm not worried about it. I'm not worried about this portion of it, okay? So I'm going to get my n plus first to factorial over 1,000, wow, to the n plus 1. Again, not going through that, you know, divide fractions, you multiply by the reciprocal. Now, what's going on here? Okay, here we know what's going to happen. We're going to be left with 1,000 down there, right? This is going to cancel out with one of these. We're left with 1,000 to the first power. But what does this n plus 1 factorial look like? Well, n plus 1 factorial looks like n plus 1, right, times n minus 1 times n minus 2, dot, dot, dot. And what does n factorial look like? Well, it looks like n times n minus 1 times n minus 2, dot, dot, dot. And if you look, all those things would cancel out if they were divided. So what am I going to be left with? N plus 1. So this is going to be equal to n plus 1 over 1,000. So we know that that's going to always be positive. So I don't even need to write the absolute value. And I'm left with this. If n goes to infinity, I'm going to get infinity over 1,000, which is going to be infinity. So since the limit is equal to infinity, which is greater than 1, the series, I'm getting sloppy there. The series, the summation, okay, diverges. Great. So there you have it. That is the ratio test. Oh, we've missed one condition. There's one condition we haven't done yet. What if it's equal to? Oops, sorry about that. We have some eraser marks we have to do here. If you look at it, if it is equal to, and I already did the work for the first one, we know that this is a divergent series, that this is divergent. But if you look at when we do the ratio test, we get that limit of equal to 1. If we look at the second one, we can easily see, just knowing p-series, that this series converges, that this is a convergent p-series. But if I show you using the ratio test, what happens, it becomes 1 over, this becomes 1 over n plus 1 squared over 1 over n squared. Apologize, I'm getting sloppy with my notation there. Limit, as n approaches infinity, we're going to get the limit as n approaches infinity of n squared over n plus 1 squared. If you FOIL this, you're going to get the same thing as you got up here. You can see that the ratio of the leading coefficients is going to be 1 because the degree of the numerator is equal to the degree of the denominator. And again, we get the conclusion of 1. So even though we know that this diverges and this converges, we get the same limit for both of them. That's why when rho is equal to 1, the test is inconclusive. And we would have to go back and use another type of test in order to determine that. So we would have to go back and use a p-series or a comparison series or one of the other series tests that we've learned. Okay, so this is a little summation or a summary, a little teaching, a little instruction of the ratio test. Please look up at the next video, which is on the root test, which is a little shorter than this one, but you'll see that it's similar in its type of conclusions that we draw. All right, so I hope you enjoyed this video. Play it back as many times as you want to. Come to class prepared and ready to rock and roll.